Looks like we can get started. Hello everybody, my name is Barbara Catinella and I will chair the sessions this afternoon. Our first speaker is Luca Cortese, who's going to give a review on gas star formation cycle of galaxies across environments.
Thanks. Good afternoon everybody. Thanks for coming back after lunch. Before we start, I'd like to thank Bianca and the organizers for giving me the opportunity to come back to Pisa and enjoy this beautiful conference. And I've been asked by the organizer to give an overview from the observational perspective on the role of the environment on affecting the gas star formation cycle in galaxies. So we'll take on a journey trying to go through the different steps of what we generally refer to the gas star formation or matter cycle, starting from the interaction between the CGM and the ISM, and then going into the effect of the environment on the atomic and molecular gas phases, looking at star formation efficiency, and then trying to figure out how we can understand how the environment affects the equation of the star formation. So I know we are all back from lunch, so if you need a siesta, the only thing I'd like you to remember is that I think it's pretty much clear now that we're moving away from a picture like this, where we're trying to put galaxies into boxes and argue on which one of the various environmental effects that we know and love or we don't love is the only one that is affecting galaxy evolution across environments. We know and we've seen throughout this conference already that this is a multi-scale, multi-phase problem, and so it's more like a picture where multiple physical processes are affecting galaxies on different time scales, on different physical scale, and so the question is more to understand how they work together to shape the galaxies that we see today. The other important point to mention is that this is a complex problem also because the environment is complex. I'm pretty sure a lot of people in the following talks will go back to this problem, what we define environment. Environment is really multidimensional. We have luckily moved away from this kind of field versus cluster dichotomy a couple of decades ago, and now we know that the properties of galaxies depends on whether you're central satellites, but not only that, also your position of the group on the galaxy as a function of the large-scale structure. Now, in the interest of time, since I only have 20 minutes now, I will primarily focus this talk on the effects on satellite galaxies. But I know that some of you later today and later in this conference will focus on the effects of other environmental metrics. So let's start and look at what we can learn about the effect of the environment on the CGM, but most clearly on the interface between CGM and interstellar medium. Why is that? Because frankly, observationally, we know very little about the effect of the environment on the CGM. As we've seen this morning, it's still very difficult to observe how the environment is affecting the CGM on satellite galaxies. Most of the information that we have is based on numerical simulations. We know that the CGM is the first phase of the gas in galaxies that should be affected by the environment. This is all the basis of what we tend to refer to as starvation. But we know now that the CGM is not always completely stripped. This is very fascinating because, for example, it's clear that to explain the properties of the small and the large Magellanic clouds in the local group, we need to invoke that the two galaxies can hold on to part of their corona to be able to explain the properties of the Magellanic streams. The other thing that I find it's extremely fascinating is that if you see here on this plot, this is a simulation showing the effect of a wind tunnel on the CGM of galaxies. And you can see that even if you just focus on the CGM, you have the formation of this beautiful tails that we all know and love that seems to diminish this jellyfish formation where we are just primarily looking at the effect on the CGM. And this brings me to what I generally call the CGM-ISM interface. So we now know that these kind of tails that 20 years ago were rare, now they are ubiquitous. This kind of step in the evolution of satellites is something that affects pretty much every satellite. Of course, the properties of these tails are different. We vary in length between, let's say, a few tenths of kiloparsec up to almost half a megaparsec in projection, meaning that some of them might be even of the level of 1 megaparsec in length. Their composition is very different. We see pretty much all the phases and also stars. We don't know yet what is the physical process that regulates this balance of the phases, and I'm pretty sure that Stephanie Tonnensen later this week will discuss this. The interesting point of view from an observational perspective is that in the last 2 decades, as an observational astronomer, people, what they've done, we try to measure the mass in detail, we try to estimate how much mass of gas has been lost by the galaxy, and comparing the two, they were matching within a factor of a few. And so the original scenario in the past was that we were looking primarily at interstellar medium stripped from the disk of the galaxy. Now, recent simulations seems to suggest that this is not always the case, might not always be the case. These states might actually be dominated, or a significant part of the contribution should come from the CGM in the halo that is lit up by the interaction with the surrounding environment. And if true, this is a very fascinating possibility, because it would show that this kind of environmental effects might allow us to figure out exactly the properties of the CGM. But again, I think this is still very challenging work from an observational point of view, and hopefully in the next decade we'll be able to do the kind of studies that we've been able to do with absorption systems in isolated galaxies on satellite systems. Most of the progress, I would argue, just following up on what Paolo has discussed earlier this morning, is on the effect of the environment of the property on the stellar medium in galaxies, primarily H1 and molecular hydrogen. We know now that pretty much H1 is affected, is removed throughout all cases of environments. If you work on different samples from a global point of view, we see pretty much that at fixed stellar mass, when we move to satellites in small halos to satellites in big halos, the amount of H1 goes down very quickly and goes down very fast. So it's no longer a question if the H1 is also stripped in groups. It's a fact, and globally we know this. The challenge is that even with the SKA, is going to remain very challenging to be able to detect H1 as soon as a galaxy goes below the main sequence. So extending this kind of studies to large statistical sample like we used with Sloan, for example, it remains very challenging. So we have learned a lot also where the gas has been removed from the early work by Veronique Kayak and co, and also Jacqueline. We know that most of the gas is removed primarily from the outside of the disk, because it's the part of the ISN that is less bound to the galaxy. But of course, with the improvement of data, we have been able to quantify this a little bit better. So this is a very busy plot. Stay with me for a second. This is let's say it's a modern way to do surface density profile or radial profiles. It's what I tend to call glorified radial profiles. It's pretty much a pixel by pixel analysis where you plot the stellar surface density of galaxies on scale of 700 parsec versus the H1 surface density of galaxies. Every panel is a different galaxy aligned as a degree of environmental perturbation. And the gray line shows you what you see, what is the average radial profile in galaxies that are unaffected by the environment. There are 2 take-home messages here. The first one is, as we also knew, when you move from the top left to the bottom right, the extent of the H1 profile shrinks because the H1 is stripped from the outside in. But the very other important realization is that even when not all the H1 is removed, the surface density goes down significantly. So also the parts where a significant amount of the atomic hydrogen is able to remain in the disk goes down in surface density. And this is going to be very important later on to try to understand the link between H1 and H2 and quenching of the star formation. Talking about H2, this is an area where I would argue much more progress has been done in the last decade. This is, I think, is the summary of what we know from a global point of view, just to start from where Paolo finished. In normal galaxies, the ISM is dominated by the atomic component. The H2 primarily contributes to 30% of the total mass of the ISM, but when you go in satellites in big clusters but also in groups, you see that the H2 over H1 ratios shoots up. So pretty much the ISM becomes molecular dominated. And the question here is, what is going on? Are we just seeing the effect of on the H1 and the H2 doesn't really care about the environment, or is there something more? And the view on this plot has changed in the last decade. As I hinted, until 10 years ago, the general argument was if I have stripping outside in, the H1 goes first. The H2 is much more centrally concentrated, so doesn't really care about the environment, and the environment, even in big clusters, is not strong enough to remove the molecular hydrogen. We know now that this is not the case. We know that the properties of the molecular hydrogen disk in satellites are affected. We have unique cases, like for example, we have now beautiful cases of clear run pressure stripping of the molecular hydrogen component. These are two recent cases, but the first evidence goes back to the early 2000s with galaxies in the Virgo cluster. And so in this case, what you see is that not only the H1 component is stripped, but also the molecular hydrogen component goes down. The fascinating thing is that we also see the opposite effect sometimes. We see an enhancement of H2 mass due to the interaction of the galaxy with the shock of with the intercluster medium that facilitates and enhances the conversion of H1 into H2. So here you have the cases of the jellyfish galaxies from the GASP team, where you have the mass of H2 per unit of stellar mass that is significantly higher than typical galaxies in the local universe. Of course, this is we think it's a transitory process. It lasts for a little while, but these galaxies will gradually lose their ISM due to environmental effects. But all I've shown you at the moment are smoking gun cases. We have very few examples where we can reach these conclusions. In general, we have more statistical approaches, like again a plot like this, where now is the same radial profile as before, but what I'm showing now are H2 molecular hydrogen surface density on scale of 700 parsec versus stellar mass surface density. And again, you see that the effect is significantly less strong as done with the H1, but you see again that when we see some galaxies, the H2 surface density seems to be significantly depleted with respect to what we expect from a normal galaxy. This, frankly, happens primarily when the ISM starts to be significantly affected within the optical disk of galaxies. So we need the environment to be very strong to carve its way inside the optical disk. But what does this mean from a physical point of view? Is this reduction of H2 surface density simply explainable with stripping of the H2? Or, going back to what Rob Kennicott said yesterday, could this be more due to the physics that regulates the conversion of H1 into H2? And this is still very much an open problem. We don't have the answer, and I just want to show you what we can do with this. So in the past, there is still quite a lot of debate on what regulates the H1 over H2 ratio. For this particular work, what we tested is the effect of either fixed mid-plane pressure or simple fixed total gas density. And so what you can do this test. You know that the H1 has been removed, so you know that the physics of the ISM has changed, you know that the mid-plane pressure has changed. Can this process alone explain the change in H2 over H1 ratio? And so again, this is a busy plot, but stay with me for a second. In the top, we are testing the mid-plane pressure. In the bottom, we are testing the total gas surface density. Again, the gray is your control sample. The black are the individual galaxies, and the red is what we should care about. This is how the H2 over H1 ratio would change only if we account for the stripping of the H1 and changes in condition of the ISM. Assuming, of course, that the H2 over H1 ratio is simply regulated by one of the two quantities in the x-axis, which might not be true. The interesting thing here is that you can see cases like 4569, we know is strongly affected by run pressure stripping, but you see that just the idea of simple H1 removal can explain the significant increase in the H2 over H1 ratio. But you have other galaxies where the red line is significantly offset from the data, suggesting that most likely we might have also an effect of the environment on the H2 or the CO better itself. Of course, I'm putting under the carpet changes in XCO factor, etc. But this is just to highlight how still challenge is to identify the physical processes affecting the ISM when we go beyond just the atomic gas phases. And the challenge here is that kiloparsec scale studies of CO in satellite galaxies outside clusters are still dramatically rare, and frankly there is no help in sight because there are no big surveys that are going to do this in the not too distant future. So with this in mind, we can now move and look at the star formation law and how the environment affects the ability of H1 to convert into star formation, or the way I prefer to look at this in terms of depletion time, because I don't think in many cases, in this case, we're really looking at an efficiency of star formation. So when we look at details, I think since the beautiful work by Pavel a decade ago, it's pretty much clear that in details, star formation or depletion is very inefficient, or depletion times are very long. We find a lot of molecular hydrogen, but we don't find a lot of star formation. And to me, it's even more fascinating, the discovery of these so-called orphan clouds. These are clouds of ionized gas and CO that are free-floating in clusters, that are not forming any stars. And this is very interesting because it shows that we are not really getting to the bottom of the physics that allow such a cold medium to survive into an environment like cluster. And perhaps Pavel will discuss this more, I think, on Friday. Moving on the disk of the galaxy and the star formation law, in the last decade, I think we reached an agreement. We reached that also galaxies that have been significantly affected by the environment follow a star formation law, but that is generally offset from your typical control sample, let's say a Things or a X galaxy. The offset is not that large, but is significant, meaning that the star formation is less efficient, or again, that the depletion time is slightly longer. The gas that is left in the disk takes a little bit longer to be consumed by star formation. This is again the observational evidence. What does this mean from a physical point of view? And again, this is a challenge because, frankly, if we look around in the local universe and we look at studies of the star formation law in galaxies below the main sequence, everywhere we find this effect. We find that as soon as we move below the main sequence, the depletion times become longer. And this is a plot that has already been shown a few times today. I'll try to walk you through this. So this is just looking at what regulates the decrease of star formation when you move from the main sequence here towards below the main sequence. Now, if the decrease in star formation would be matched equally from a quantitative point of view, but a decrease in H1 and H2 global content, your purple and green line would be on the one-to-one relation. They are very close to the one-to-one relation, but they are offset. And we can account for this difference by an increase in depletion times when we go to below the main sequence. Suggesting again that this effect that when we go below the main sequence, regardless of environment, our depletion times are longer, might imply that what we are seeing is more an effect of what is the physics of the ISM in this environment, regardless of how we got there. And this, hopefully, it's something that we can make progress in the next few years. This brings me to the last part of my talk, and to discuss the part towards full quenching. The point here is that what we've discussed so far are what I would argue just the early stages of quenching. Once upon a time we were thinking, oh yes, we strip the gas, the galaxy is dead, it's done. We now know that even in big clusters, this is a way too simplistic case. I show you that we have everywhere after first pericenter a significant amount of gas left in the inner part of the disk. And as you can see here, and we have already discussed that star formation proceeds slightly at a less efficient stage, so depletion times are longer. Meaning that if we take a cluster like Virgo, the satellites after first pericenter will have a depletion time that is of the order of a few billion years at least. So longer than a crossing time. So this means that it takes more than just a crossing time to a typical galaxy of 10 to the 9 solar masses or higher in a cluster like Virgo. Of course, if you go to the local group, it scales down accordingly to completely quench the star formation. And so the question is, what's going on? And I think this is one of the big challenges for the next decade or so, to try to be able to trace the environmental evolution of satellites after first pericenter. GASP had done a fantastic work on the early stages of quenching. We now need to figure out what's going on, because it's pretty much clear that if we remember my very first slide, we have multiple physical processes affecting galaxies. And so wire and pressure might be the very first thing to affect the ISM. It might not be just the full picture. And I just want to finish this talk highlighting one prospect to make progress on this. This is a new Muse large program in combination with ALMA and ASCAP to try to figure out what happens to the ISM after first pericenter passage. So the program is MOVE, which stands for Muse and ALMA Unveiling the Virgo Environment. We are targeting 40 galaxies in Virgo, and you can think about this as funks, same scale of funks, same kind of data, but in the cluster environment, to try to understand the physics of the ISM in these extreme cases. We are at the early stages, we're just 20% complete, but in the 5 minutes I've left, thanks Barbara, I just want to show you two big surprises that we're finding. The first thing is that we're finding that star formation ionized driven outflow are everywhere in galaxies post-pericenter. This is something that personally, I worked on Virgo for quite a long time. I honestly didn't expect, and most of these galaxies are below the main sequence. These are galaxies that some of you would call passive, simply because they are below 0.5 dex under the main sequence. They've lost a lot of gas, but you see all these beautiful bipolar streams of star formation driven outflows. We don't have AGN there, we have a lot of gas that is going to be ejected. And so this is super interesting to me because it might show that even after the first phases of stripping, the gas that is left in the inner disk might be affected by feedback there. We're not talking about a giant M82-like starburst, but still we're talking about system where star formation rate surface density in the inner parts is high enough to trigger this kind of outflows. The other opposite surprise is to try to figure out how the ISM behaves when we are after first pericenter. This is for those of you who have not worked on Virgo, this is a completely anonymous galaxy, and was an anonymous galaxy for me as well. This is one of these galaxies for which people have tried to determine quenching time scale, and everybody seems to agree that was stripped, let's say, around 500 million years ago. It doesn't matter for this talk. What matters is that these are the contours of the of what's left of the H1 disk at 1 solar masses per parsec square surface density. The CO, so the H2 at 5 solar masses per parsec square is the same. And so if you do your H alpha profile, you see that your star forming disk is shrunk and it's very truncated, consistent with this idea of outside-in stripping and with star formation only be present in the inner 0.5 effective radii of the galaxy. But then the beauty of Muse is that you can actually play with the data cube. And what we are finding is we are finding ionized gas all over the place outside what we generally call the truncation radius. You see that we extend with Muse up to 1.4 effective radii, and then if we follow this up with deep narrowband H-alpha imaging, you see that this very kind of exponentially declining surface brightness profile in H-alpha extends at least up to 2.5 effective radii for a galaxy for which most of all the ISM should have been stripped a long time ago. This has nothing to do with star formation. This is much more consistent with the diffuse interstellar medium, and our working hypothesis at the moment is that we might be seeing the replenishment of the ISM due to stellar evolution. But of course this is still work in progress, but again to highlight how targeting the past first pericenter parameter space can allow us to discover a few surprises. And this is all I wanted to say. Here you see the kind of summary of the 4 areas I wanted to discuss. I also highlighted in red what I think are going to be the primary challenges, both from a theoretical and observational point of view, and I'm happy to take any questions. Thank you very much.
Time for questions. May I encourage questions from students? Okay, so let's open to everybody, I guess.
Very nice presentation, Luca. I have a curiosity regarding the last part when you show us the outflows. I wonder about the velocity of this kind of gas. Is it H-alpha, right?
Yes.
So how much is the velocity that is going out?
200 km per second.
Okay, so do you think that this galaxy will lose the gas?
No.
Okay.
No.
So it's more consistent with a galactic fountain in that sense, or?
It's tricky because you are in a cluster environment. So the question is, once the gas goes up, whether what's left of the wind, depending on where the galaxy is, could either prevent the gas to fall down, or by the time the gas falls down, the galaxy is gone. So that's a very interesting question, and we are trying to model this, because also we should be able to trace also the neutral phase of the outflows with the sodium.
In the vertical study, when you showed that if we assume not or assume the H1 is stripped, the H1 to molecular conversion different, could you explain a bit more what does it mean, assuming it is stripped or not stripped?
So this is just to show the diversity of cases. You see that every galaxy is different. Of course, it depends also on the assumptions that you are making. The point I'm trying to make here is that I don't think we understand yet the physics of the conversion of H1 over H2, so what is really driving it, and then how whatever environmental processes, because I intentionally put it under the carpet, I didn't use any particular favorite process, affects the ISM. This is just to show that in some cases, let's say the bottom right, you could explain the change, the dramatic change in H2 over H1 just via H1 stripping and not changes in the H2, while in the top galaxies, you see that you need also to get rid of a little bit of the H2 to move the red line back on the data.
Thanks for a great review, Luca. I would have two questions, but I'll make one. I don't want to take the space. Regarding this, exactly, do you have for this WATT sample the ratio of the molecular over stellar mass?
Yes.
Because that would be very, very interesting to see, because...
So this is resolved. So this is, it's not the ratio, but it's one versus the other. So we can definitely do the ratio.
Yeah. So actually, you see the same. You mentioned that the effect that the molecular gas fraction is very high in some jellyfishes can be in a specific phase, let's say. But this is also actually what you're seeing here, that the molecular over... No, you see the opposite, actually.
I see the opposite.
Okay,
but
so
look,
Virgo is the opposite.
I think is that you don't have, let's say, a gasp-like jellyfish population in Virgo.
No,
The
exactly.
environment is less extreme.
That
and
was
so
my second question.
I think the challenge is to figure out, let's say, where we are when we put together the galaxy population. I don't think we are there yet.
Yes. So if there are no other questions, that was my second question, exactly. That is, the other issue, how long it takes to strip them. Is it one passage enough or not? Again, Virgo is not... It's maybe a special case in the sense that it's not very strong stripping. What we see from the post-Arbus population, but this is a work that Ariel Verle did, and okay, it's actually 0.3, but we looked at also in GASP, is that from the post-Arbus feature, you can exactly time how long it took to strip the whole gas. And in all the post-Arbus cases, it was never more than a few hundred mega years.
Yeah. So two things, absolutely. If you go back also to the plot that Paolo has shown for the local group, when you go to low mass, and that threshold depends on the halo you are working with. So in coma, even at 10 to the 9.5 galaxy will be stripped like this. I think for me, my personal view is that clusters, we are getting there. But a Virgo environment or a Fornax environment gets us closer to the group environment, which is most of the statistics of satellites in Sloan and other kind of statistics. And I think that getting the gas for this kind of environments, understand the physics of the ISM in those kind of environments, could get us closer to figuring out all this quenching time scale and quenching our issue.
Any more questions?
About star formation law and the H1 deficient galaxies.
Yes.
What about putting them on the correlation between the total gas surface density and star formation rate surface density? Because you are plotting against the molecular.
Yeah. So in that case, it doesn't really change because the H1 has been, regardless of what's going on with the H2, the H1 has significantly been more affected than the H2. So even if you do the total gas is dominated by the molecular component in those kind of galaxies.
How do they compare with the non-deficient, non-H1 deficient gas?
The offset would be even larger. If you do the total gas for your control and the total gas for the H1 deficient, of course the offset will be larger.
Okay, let's thank Luca again. And our next speaker is Blok, talking about local density H1 environment of nearby galaxies as revealed by me.
Okay, great, thank you. So in the next 50 minutes or so, I would like to share with you some recent results that we've obtained with Meerkat, specifically about the low column density H1 around nearby galaxies. As part of the Mongoose survey, not everybody of you will have heard of that survey. So what is it? It's a Meerkat large survey project to use ultra-deep H1 observations of nearby spiral and dwarfs to study the accretion of cold gas and its link with star formation. Of course, you've heard a lot about it already today and yesterday, and I hope to share with you some observational results on that. Specifically, we've been observing 30 nearby galaxies at 55 hours of observing time per galaxy, so roughly 68 days of Meerkat time. So these are indeed some of the deepest H1 observations, resolved H1 observations currently in existence. If you're interested in some of the survey aspects, I encourage you to look at the website or read the survey paper, which has been accepted for publication, is available on archive there. Well, you've heard a lot already about the baryon life cycle, so I won't go into a lot of detail here, just to say that the two aspects of the baryon cycle for which H1 is relevant are, of course, the diffuse H1, the less than 10 to the 19 atoms per square centimeter component, mostly found outside, between quotes, the galaxy, outside the stellar disk, indications of accretion and interaction, as we've already seen. And of course, there's the aspect of the high resolution H1 in the inner disk, where you would like to study things like star formation. I will mainly be concentrating on the aspect here, the outer part, and its links with accretion and interaction. It's a survey done with Meerkat. Meerkat is essentially the forerunner of SK-MID, located in the Karoo semi-desert in South Africa. Lots of details there. The main point, takeaway, is that it has a very good array configuration, which combines the ability to image at high resolution, but also retain the high column density sensitivity that you need to explore the low column density universe. I can sort of illustrate it in this plot, which shows you the resolution on the horizontal axis versus the column density sensitivity, all put on the same scale. All the dots are essentially all the pointed H1 observations of nearby galaxies from the last 20 or 30 years. The points up here are interferometric observations. The points down here are single dish observations. And the blue line here is the sensitivity curve that we are getting with Meerkat. And you can see that, of course, at every resolution we are probing deeper in column density, but maybe more interesting is the part down here, which shows that we are looking at essentially column densities that you normally would only derive at single dish telescopes, but we are observing them actually at a resolution that is 50 to 100 times better. That opens an entirely new area of parameter space that really has not been explored before. Cold gas accretion, we've already heard a lot about it this morning, so I won't go into a lot of detail here. I will just concentrate on the H1 aspect here. Essentially, people have been looking for cold gas accretion, H1 accretion for decades now. Never found it, or at least not in the numbers that are needed to sustain the star formation rate. So the most recent survey was the Halo gas survey, looked at galaxies, so low column densities with the Westerbork telescope down to about 10 to the 19. Didn't find much, and so the question now is, if H1 accretion is indeed happening, where do we have to look? Well, most likely low column densities. Simulations can help us support that. Here's just one example of a simulation showing you, essentially all the neutral hydrogen. This is what it would look like at halo gas sensitivity. So you're missing out on most of the H1 in the outer parts. And you really want to go to something like a few times 10 to the 17 to really start picking this H1 up. And that, of course, is what we are aiming to do with the Mongoose survey, or what we are doing with the Mongoose survey. We are probing down in the 10 to 18, 10 to the 9, 10 to the 17 regime at kiloparsec resolution or better. The sample, 30 galaxies, like I said, varying from dwarf galaxies around 10 to the 7 to massive spirals around 10 to the 11. Solar masses in H1, selected to be in a non-cluster, non-dense environment. So this is a different environment than we've heard about before, Virgo, Fornax. This is not what we're probing here. And important, we have high velocity resolution, as Paolo was already pointing out. That is very important to say more about the state of the H1. This is just a cartoony way of showing what the sample looks like on the same physical scale, a 10 kiloparsec bar down here. So we really are probing tiny dwarfs to very large spiral galaxies. An example of the quality that we're getting with Meerkat. Here's an H1 map of NGC 1566. This is the previous generation of observations. So 30 arc-second-ish type resolution. And when we stare at this galaxy with 55 hours with Meerkat, you're seeing this. So there's a lot of detail here. This is, of course, is also one of the galaxies that we saw yesterday, imaged by JWST. You see central absorption here due to the AGN. Lots of structure in the outer disk. I'm not going to go into these aspects. I'm going to concentrate on the outer part, the low column density part. Then the galaxy looks like this. The yellow contour is something like 3 times 10 to the 17. So we really are going very deep, and you start seeing things of, hints of a bridge with this galaxy here, 1581, that probably had an interaction with 1566. Lots of dwarfs are showing up as well. And the high velocity resolution also enables us to do things like, looking at the moment 2 is the velocity dispersion map, where we are actually seeing the tail probably caused by this dwarf as it passes over the disk, having stirred up the H1, resulting in this increased velocity dispersion. So lots of room here to study the dynamics of these systems. What we're also finding are small dwarfs, like this one here. This one turned up by accident. It's a dwarf with, with 10 to the 6 solar masses in H1, baryonic mass of also about 10 to the 6, and this really is one of the lowest mass, H1 mass dwarf galaxies detected beyond the local group, because this thing is at 20 megaparsecs. So we really are starting to do, local group type science now also in more distant systems. It's a very low column density dwarf, peak column density of about 5 times 10 to 19. We can rule out that there's a large high column density component hidden here that we're not seeing due to the beam size. It really is a low column density disk. There's a tiny amount of star formation here. And when you go through the modeling, you can work out that this dwarf is probably on its first infall in the Dorado group around 1566, and probably will be destroyed or stripped in the next 100 mega years or so. Nice thing, of course, is that we can now start taking these dwarfs at 20 megaparsec and start putting them in plots of local group dwarfs, things like the baryon fraction versus the baryon mass. This is the first dwarf that we've explored, but there are many more in the sample, so we will hopefully start populating this plot. And those of you that looked at AstroPH this morning will already have seen that this paper was accepted recently and is now available for you to have a look at. Just show you a few pretty pictures of some of the other galaxies. 5068, a very nice star-forming disk, high column density H1, with an outer disk here that has a column density a factor 10, 20 lower. An H1 mass of this outer disk is also only about 10% of the total H1 mass. And well, this looks like accretion is happening of something. We're not sure what. There are no signs in the stellar imaging of disrupted dwarfs or things like that. So this is still very much something that we are working on with some dynamical modeling. An Edge-on galaxy here. The motley aspects that you're seeing here is not noise. These are actual the H1 complexes that are being blown out of the disk. It's the galactic fountain in action. So this may be a good example. Start looking at this galactic fountain-driven accretion that we talked about this morning. Again, work in progress, where we're trying to look at the dynamics of these clouds in that galaxy. And of course, there's this triplet, NGC 40881 triplet. It looks really disturbed. But that's only because we're looking at it at very high column density sensitivity. If you were to look at this with a column density sensitivity of 10 to the 20 or so, something that we're all used to, these would just look like 3 isolated galaxies. It's only when you push down to the 10 to the 18 level, which is what all these clouds are at, that we are starting to see these interactions. There's no sign of, like with the jellyfish galaxies where you might expect to see star formation here and stellar disturbance. There's no sign of that. This is pure H1. And this may be sort of reminiscent of this kind of NGC 4631 feast observation that was shown earlier. Last 5 minutes, I want to talk a little bit about a comparison between Mongoose and the simulations, because with the Mongoose data, we now for the first time have the column density sensitivity and the resolution to make one-on-one comparisons with the simulations. The one sample that we have been using as a comparison is the Ramesh et al. Sample, a detailed study of Milky Way-like galaxies from TNG 50. And we have 4 galaxies in our sample that essentially obey the same selection criteria as the Ramesh et al. Sample. So what we've done is we've taken these 4 galaxies, observed them, we did our usual processing, made moment maps, and then with the help of Antonino, who has really been doing all the heavy lifting in this, taking the TNG, selecting 20 galaxies at random, more or less, from that Ramesh et al. Sample, and essentially pretend that we observe them with Meerkat. So we derive the H1 distribution after the usual H1, H2 partition, etc. Put them at the same distance as the Mongoose galaxies, 20 megaparsec, and essentially insert them into a Meerkat cube, noise cube, and then put them through exactly the same processing as we did with the real galaxies. So what we are getting are essentially what these TNG galaxies would look like if they were 20 megaparsecs and observed at Meerkat at 55 hours. Well, those of you who look at H1 maps more often can already see some differences here. There seems to be a lot more structure out in the field. And of course the question is that a real difference? How can we quantify it? Well, the first test we can do is look at the column density distribution and the velocity dispersion distribution. Left is the column density. The green histogram, or the probability distribution, is that from the observations, the Meerkat galaxies. You can see a very strong peak, around 10 to the 20 and a bit, and then a decline. Our 3 sigma sensitivity is actually around about here, just above 10 to the 18. So, this is all very significant column densities. You can see that in the TNG simulations the things are different. We don't see this peak at 10 to the 20, but rather we see a sort of general increase towards 10 to the 19, where we see a lot of H1 that we don't see in the observations. If we look at the dispersions, we're also seeing a difference here. The observations peak around about 10 kilometers per second, with the tail towards higher dispersions. But you can see that the tail for the simulations is much more extended, and this is shown better on a linear scale. You can see that we are seeing the dispersions up to 120 kilometers per second or higher. And these tend to mainly occur in the outer disks of the galaxies, of the simulated galaxies, which is of course not what we are seeing in real galaxies. And these high dispersions are essentially where the filaments sort of hit the disk and disturb things. But again, we don't see that in the observations. Now, how can we quantify this? Of course, anybody can see, yeah, there's more fluff in the field, but you want to quantify this. So one thing we did, this is a very, very simple parameterization, is essentially to look at the fraction of the galaxy H1 area below 10 to the 20. So what fraction of the H1 disk is at a column density below 10 to the 20. Essentially, if that fraction is small, then you are dominated by a high column density disk. If that number is high, then you are dominated by a fluffy, low column density structures in the outer field. Observations live here, so they are dominated by, they are more or less a well-formed high column density disk with not a lot of faint outer stuff. You can see that the TNG are actually in the other part of that regime here. They are dominated by lots of stuff in the outer field. And when you sort of split this in half, arbitrarily at this value of a half, You can really see that there are these regular galaxies that don't show a lot of outer field fluff, and there are these irregular ones which still show those filaments that we know from the simulations. The 4 boxes here are the observed galaxies. So you might say, well, that's it, problem solved. We just happen to have observed 4 of these regular galaxies, and there's still plenty out here to be discovered. If only we observed more galaxies. Could be, but that's not quite as simple as that, because of course one of our questions was, well, does this have to do with environment? Is this because of different numbers of satellites? Is this why we get these filaments out there? And we did a very, very simple, naive parameterization of that, essentially count the number of H1-bearing satellites above a certain mass within a certain volume around the target galaxy. You can see that the regular, so the ones, TNG galaxies, the ones without all the stuff in the outer field, they essentially have no satellites. The ones that are irregular have a larger number of satellites, up to 4. And the observations actually have a preference to be in that regime. So we have essentially the compact observed galaxies have a set number of satellites only consistent with the irregular fluffy TNG galaxies. So these are 2 contradictory outcomes. This is, of course, it's all small number statistics. We are still building up our observed sample. We want to extend this also to lower masses by looking at further TNG galaxies. But it's very interesting that we have lots of stuff to do. And indeed, it's not just accretion, it's just filaments, it's also environment. It's a whole mishmash of things like, look, I was just referring to that is relevant for the environments for the evolution of galaxies. So just summarize, the survey is underway. We are still observing, but these are some of the first results that are now coming out of it. We've seen examples of possible accretion, but of course accretion in this case is a very loose term. It's not just an accretion as in primordial gas, but also minor satellites, environment, etc. We are starting to pick up low mass galaxies outside the local group, which would be interesting for cosmology and evolution of dwarfs. And there's more to come, so keep an eye out on AstroPH. So thank you.
Thank you. Questions?
Yeah, so if you compare the total amount of gas in TNG in a big box to the total amount of gas that you see, do you see about the same? So you see it in satellites and not in diffuse gas?
If we look at TNG as observed by us, then those numbers are roughly consistent. Yeah, there's not a big discrepancy. Something, yeah. Probably more environmentally dependent rather than that's related to accretion and things like that.
Yeah, I was wondering if you compared the number of satellites with something like fire simulations that model cooling to low temperature, so maybe those form more substructures.
That'd be interesting. Yeah, we have the fire ones. We haven't really looked at the satellite distribution there yet, but I think that is probably something we can still do, Antonino. So that's, yeah.
Spectacular data, and I was wondering about the bubbles that you are resolving. Are you doing anything about that? Connecting with stellar feedback, but even pH distributions and so on?
The answer is no, but we would like to. I mean, we are really person power limited in this case. I mean, like you can probably see this map.
Yeah.
There's 20 papers in this map alone.
Yeah.
And we
what
love
is
to
your
do it.
closest target in distance?
The closest in distance is about 3 megaparsecs.
Okay, let's talk.
Yeah.
Thank you. I'm wondering whether the mock observation process also changed the properties that you compare with the simulation and observation, like would the process of mock observation also change the distribution of quantum density, and how is that change like?
it's a good point you're making, and yes, if we were indeed looking at if we indeed were limited to looking at differences at the 10 to the 17, 10 to the 18 regime, I would be equally worried as you. But you can see that the difference, occurs at the 10 to the 19 level already, and that is something that we are observing with the signal to noise of many tens already, and it's really did this work which already have been done with Halo Gas or even the Think survey almost, if only we had trusted them, if it had higher signal noise in them. But so I see your point, but in this case I'm not worried about it.
Maybe time for another question while the next speaker gets set up.
Hi, do you plan to study also the continuum?
Yes, we have very deep continuum of doses, obviously, as well. We have the continuum that, of course, you get when you make the H1 cubes, which you subtract, but we also have in parallel 4K, so 4,000 channels over the entire meerkat band. So that's a few hundred megahertz that we are sort of starting to process now. And yeah, I didn't have time to show anything, but the images look spectacular as well. So yeah.
Okay, let's thank Erwin again. And our next speaker in this session is Simone Veronese, continuing with Mongoose, talking about stacking ultra deep H1 observation with Mongoose.
So hello everybody, I'm Simone Veronese, I'm a PhD student at Astron and at the Captain Astronomical Institute at the University of Groningen, and I'm working with Erwin de Blok on the Mongoose survey, and today I'm here because I want to discuss with you the following question, which is where is the neutral gas, and the answer that I'm trying to provide to it, which is searching for the H1 around Mongoose galaxies via spectral stacking. And the reason why we care about the neutral gas, as we have already heard today, is because it's the raw fueling for star formation. Sure, molecular gas provides stars, but in the first place you need the H1. And actually a plot that I was surprised hasn't been shown today is this, where we have on the left the cosmic star formation rate of the universe as a function of time, and on the right we have the cosmic H1 density. And we can see that if we focus on the first 3 giga-year of the universe, as more and more stars are produced, the H1 content of the universe decreases, whereas if we look at the last 10 giga-years, it seems like the H1 content is reaching a plateau, even though stars are keep produced. So this is one of the evidences that led people to think that there is the need for galaxies to accrete gas from somewhere in some way in order to have this plateau in the H1 content. But the problem is that observationally it's not easy to detect this H1, and the reason is because we need column density of about 10 to the 17, which is doable with single dish observation, but we also want spatial resolution because we want to resolve the structure of the H1 around galaxies, because we want to distinguish between what is actually a H1 cloud due to pristine gas and what can be a dwarf galaxy or a feature because of a tidal interaction or an interaction between galaxies. And if we can achieve the spatial resolution with interferometer, we can achieve the sensitivity with single dish. And so we have the problem that the H1 related to accretion is likely living in a region of the parameter space which is unexplored yet. And so this is why recently many efforts has been put in developing new telescope and new survey in order to really start to see what is the H1 looking, how is, well, you understand, in this region of the parameter space. And this is why we have something like Mongoose that, as Erwin has said, it's a large survey program on the Meerkat telescope. And thanks to Mongoose we have, and especially thanks to Meerkat, we have for each of these 30 galaxy multiple resolution in the cube from 8 to 90 arcsecond, but also multiple sensitivities from 8 times to the 19 to 8 times to the 17. And so now we can really probe the H1 in this regime. But most importantly, as Erwin has already mentioned, we can finally directly compare simulation and observation. So here again are these 9 TNG50 galaxies to be simulated as being observed through Meerkat, which have this beautiful H1 structure around them. The column density is 10 to the 19. Then we go to the real galaxies and we don't see all those beautiful structure, even though the column density sensitivity is at least 1 order of magnitude lower. And so the question is, where is the neutral gas that simulation are predicting that must be there because we know that accretion should happen? And so I tried to answer this question employing the large data volume of the Mongoose survey and apply the spectral stacking technique, because spectral stacking is a way to push the sensitivity of the data even further down, and hopefully by doing so we should be able to detect the signal from this low column density H1. And what spectral stacking consists is basically you take spectra along different line of sight, you co-add them, and if everything goes correctly, the noise goes down, and if there is a signal, it can emerge, because otherwise it's invisible. I have to stress out that this technique has been applied mainly to look for mean properties of galaxies. So you basically have multiple galaxies in the field, you co-add them spatially and spectrally, and then you look at what is the mean properties of the H1. But here I'm doing something differently, because we are trying to detect the H1 around a single galaxy, which is also resolved. And the way we are doing this is basically we take the cube, we regrid it so that the pixels are spatially independent, we blank the galaxy emission for obvious reason, and then we divide the field of view in this grid of cells. And so here, for example, we see the target galaxy being blanked out. The background is the collapse of the cube along the spectral axis, and the pixelated morphologies because of the regridding. And then we stack within each square the spectra. So for example, for this configuration, for this galaxy, we would have a total of 225 stacked spectra that we run through a one-dimensional source finder that is designed to perform a statistical analysis on the peaks in all those spectra in order to distinguish what is a noise peak and what is likely a genuine emission. And how it works is basically applies a smooth and clip procedure on the spectra, then look what peaks are above a given threshold, and put all those peaks in this parameter space where there is the peak versus total flux, peak versus mean flux, and total versus mean flux. And then the noise should clusterize in this distribution, and whatever it's not a noise, it's an outlier of this distribution. And if the signal to noise ratio of those outliers is above a given threshold, then it's very likely a genuine emission. And people that are familiar with this will recognize that this is just a very simplified version of the SOFIA source finder, which has been developed by Paulo Serra and Wes Meyer. So we are just doing, we haven't invented anything new. There are common tools that people are using. We just readapt them to address our science question. So given the complexity of the algorithm, we tried and tested on the TNG50 data. And here, for example, I showed the result on one of the TNG50 data where we have 29 detection, which means there are 29 cells, which are the colored boxes here, for which we have in their stacked spectra at least one reliable sources. And here I have an example of 4 of these sources. And the reason why we use TNG50 data is because in simulated galaxy we have control of all the priors, so we can actually go back and see if whatever is extracted from our source finder it's real or not. And then given that this successful outcome of this exercise, we move on to the real data, and we actually found only 13 detection in 6 cubes. We don't have all the cubes because the survey is still ongoing. 9 were not visually identified, and 4, which are the 4 here, have been also visually identified in the cube, because we know the spatial location of the cell, we know the spectral location of the source, so we can go back to our cube and see by eye, knowing where it should be, if we can see something popping up. And indeed, for these 4 detection, we were able to see it in the cube. The noise level is 10 to the 16, so actually we have pushed the sensitivity even further down, but there is still a mismatch between simulation and observation, so this neutral hydrogen is still missing somehow from the data. And so the answer still, the question still holds, where is the neutral gas? And one answer could be that the gas is there and we are doing something wrong, we observer. But actually, when I applied my stacking algorithm on the TNG50 data, I was able to extract H1 outside of the gaseous disk. So actually it seems that it's working, and also from what Erwin has shown before, directly compare simulation and observation seems to point out that the simulation are over-predicting the amount of H1. And still we are still far away, in my opinion, in trying to provide the answer on where is this gas that is accreted onto galaxy coming from. And so we think that actually as I already spoiled, the answer is that the gas is there because it must be there. Data are also telling that accretion is happening, but it's not in the state predicted by simulation. And for instance, we think that the H1 radial profile is exhibiting a sharp cutoff. So instead of being 10 to the 17, as one could imagine, goes immediately down to 10 to the 16 or even lower. And so this is why we don't see it with Mongoose. And there are recent single dish observations that support this view. And also, in order to confirm this, we are now currently doing a detailed radial profile study of the Mongoose galaxies to see if we can see this cutoff. And an explanation can also be that the neutral component survives only close to the gaseous disk. So the CGM, the IGM, doesn't have neutral gas at all. It can be ionized. And the reason is because the column density of the neutral component is so low that it's no more self-shielded by the UV background, and so it becomes ionized. And here are the conclusion, and I guess I'm perfectly in time, so I have a few questions.
Do the simulations include intergalactic UV view?
Include
the intergalactic UV background?
I think so, yes, they should.
They should?
I hope so.
I'm wondering, is the same kind of noise inputted in the simulation data, would that explain some of the inconsistency between simulation results?
So I don't think so, and the reason is because given one of the outcomes of this exercise was also to looking at the Mercat noise and how it looks like. And so we compare Mercat noise with Gaussian noise. The Gaussian noise is injected into the simulation, while here we have real noise. And so we compare the purple histogram is the Mercat noise, the blue is Gaussian noise. If you take the ratio between the beams, you can have the level of Gaussianity. And you can see that the Mercat noise is Gaussian up to a level of 4 sigma, which is the dashed line. And then they start to, the two histogram becomes to diverge. And we also quantify the amount of excess of non-Gaussian noise pixel, let's say. And this is 10%, so 5% here and 5% here. So Mercat noise is Gaussian up to 4 sigma and is not Gaussian for 10% above 4 sigma. So in my opinion, I guess we can assume that the Mercat noise is Gaussian. Since it's Gaussian, also the noise injected into the simulation, they basically match, and so any difference is not because of the different distribution of the underlying noise.
But in interferometry, usually what we vary is the noise correlated, like the dirty beam patterns.
That's why we do the regridding, because we want all the voxel in the queue to be independent, so that's why we regrid. So 1 pixel now is equal to 1 beam, and I haven't shown it, but if you look at the decline of the noise in the stack spectra, it goes down as the square root of n, as you expect, given the Gaussian distribution.
Hi, quick question. Do you have any background quasar in your field of view?
Yes, we have a lot of them, and this relates also to the question about the continuum. What I'm also doing is have this machinery in place. I'm stacking along the line of sight of the quasar to look for absorption, and we are currently limited by the amount of time needed to produce a continuum map, but since the survey is still ongoing, whenever I have a continuum map, I'm doing this.
Simone, thanks a lot for the nice talk. When stacking, are you applying any sort of weighting scheme when you're stacking on the? So
we use the common 1 over sigma square weighting. Actually, we test also the no weighting, so just a pure mean. And the outcome was, the difference in the outcome was negligible, and this is exactly related because Mercat noise is basically Gaussian. So,
thank you.
But we do it. We did it.
Still have some time if there are more questions. If not, let's thank Simone again. And our next speaker is Nicholas Luber, talking about Cold Gas Chronicles, tracing galaxy evolution in the cosmic web.
I hate how I sound over microphones. I guess I can't get away from it this time. Isn't that a human thing, though? Right, don't we all? I feel like that was a study somebody did. Please just let me present. Okay, so I'm Nick Luber. Hi, nice to meet you all. I'm a postdoc at Columbia University, and I'm going to tell you the Cold Gas Chronicles, tracing galaxy evolution in the cosmic web. Don't worry, I'm not clever enough to have thought of that title. That was ChatGPT, but the work was all me, so we're good. But it wasn't all me. It was also these lovely people who have contributed to some part of everything that I'm going to show. All right, so the first 24 slides, which, as Jacqueline remembers my PhD defense, which was 45 minutes and lasted an hour and a half, are going to be about chilies and stacking. So to not take up too much time, I'm going to just talk about them very briefly. If you want to ask questions at the end or talk to me afterwards about them, more than happy to drone on about both. So chilies is a 1,000-hour survey done with the VLA in B array over a small field of the cosmos field. It's a single pointing, and it has the ability to resolve and detect H1 in galaxies out to a redshift 0.5. The full survey has been calibrated and imaged. Caveat, 20% has to be reprocessed for offline issues. And here is just some idea about the quality of the data. The data is good in the good spots. In the less than good spots, for example, 1170 to 1300 megahertz, it's less good, but it's good enough to use. Again, you can bug me about that more later. Cool. So also, we will be using H1 kubelet stacking for all of the results I'm going to show. Briefly, you take an input catalog of galaxies, you extract a little kubelet in both angular and redshift space around your galaxy of choice. You then convert these kubelets into luminosity units, correct for primary beam attenuation, and then I average all of the kubelets with a inverse variance weight. I then velocity smooth by factor 2, fit a line to the emission-free channels, subtract said line, and measure the H1 mass within a 60 kiloparsec box. Just to give you an idea of what the spectra from these galaxies look like, so you have an idea of the signal-to-noise regime that we're playing around with. Here are 4 detections for blue galaxies across a continuous redshift range in the Chili's field. Okay, background done. Let's ask a question. How does H1 content evolve from massive galaxies out to intermediate redshifts? So, for massive galaxies, I'm going to consider those with, that have a stellar mass in the range 10 to the 9 to 10 to the 12.5 solar masses. For 2 reasons. I think 10 to the 9 is a good cutoff for a massive galaxy, and because Cosmos claims to be complete for the redshifts that we probe for those stellar masses. For intermediate redshifts, what I'm going to show for all the Chili's results is going to be in the redshift range 0.1 to 0.48. Got it? You guys aren't a very good audience. All right, so really cool that since Chili's is such an excellent survey and was so well reduced, is we have excellent sensitivity and can further divide our massive galaxies into 2 mass bins. I'm going to call the intermediate mass bin, those with stellar masses 10 to the 9 to 10 to the 10, and high mass bin, those with 10 to the 10 to 10 to the 12.5 solar masses. Also, for all of the stuff that I'm going to show today, I'm limiting it to the blue galaxies, which I will define as those with an NUV minus R color between the range, -1 to 3. So, some results. So here we see the H1 mass and the H1 mass fraction, which is simply defined as MH1 over M star, for the intermediate mass galaxies, which are the black points, and the high mass galaxies, which are the green points. And seen both in H1 mass and H1 gas fraction, the intermediate mass galaxies have very little change over this redshift range, while the high mass galaxies at increasing redshift are more H1 rich. Super cool. So now thinking about this and thinking about the point of galaxy evolution and star formation, we look at the star formation rate for these same sample of galaxies. To do that, we use the Chili's continuum survey, so some commensurate data, and we stack radio continuum to get an estimate for the star formation rate. For the same sample of galaxies, we find that the high mass galaxies have a higher star formation rate, makes sense, they should, and a lower specific star formation rate, But what I find most interesting is that the star formation rate for the intermediate mass galaxies is increasing at a faster rate than the high mass galaxies. So we put these two quantities together in everybody's favorite timescale, the H1 depletion timescale, which we will simply define as MH1 over star formation rate, and we get this. So for the intermediate mass galaxies, over this redshift space, we find that with increasing redshift, the depletion timescale is decreasing. But for the massive galaxies, the depletion timescale is remaining constant. Super cool. Now, we want to think about this in terms of the total gas content. And to do that, we are going to go to what was alluded to with our first talk of the conference, some results from Nick Scoville, and compare them to total gas masses via dust emission. Okay, so how we do this is we add some dashed lines to this plot. The dashed lines are scaling relations from Scoville et al. 2017. We're using dust emission. They calculate the expected total gas mass for a given stellar mass and star formation rate. When we do this, we find that for our intermediate mass galaxies, first, the H1 content is sort of in line with the depletion timescale. It's, the majority of the gas within the galaxy, so the depletions have similar timescales. However, for the high mass galaxies, we find that if we take the Scoville results as true, that the H1 gas is only of order 10% the total gas mass of the galaxies and has the opposite trend in redshift. So from this, I would say, taking the comparison with Scoville as base truth, that for intermediate mass galaxies, H1 is being replenished, some other process is responsible for the slowing down of star formation rate. For high mass galaxies, H1 is not being sufficiently accreted onto the disk of the galaxy, which could be the cause for the decline in star formation. However, what I think the big takeaway from this is that one must care about H1, so I hope you've all loved this H1 session when thinking about the evolution of star formation rate in order to make sense of these scaling relations. Now, the title of this talk said that we were going to talk about the cosmic web, so let's do that. More specifically, we're going to look how Chiles compares to TNG 100. All of the simulation work is I've never even opened a simulation, which is perhaps a personal flaw, but we can discuss that later too, was done by Farhan Hassan, who is a graduate student at New Mexico and is about to start a postdoc at Johns Hopkins, or Space Telescope, Maryland, somewhere in Maryland. So here we, again, are just looking at blue galaxies, and we're looking at the same sort of gas fraction, and we stack galaxies in the filaments, at the filament boundaries, and the voids. We define the cosmic web using disperse, the discrete persistent source extractor. Everyone who studies the cosmic web now knows that this is being very commonly used as something to define the filamentary network. We define in the filaments is a 0 to 2 megaparsecs from the spine of the filaments. The boundaries of the filaments is 2 to 4 megaparsecs, and the voids is 4 to 20. This is somewhat motivated by the fact that for both the simulations and the observations, the 50% point of the distribution of galaxies happens in the range 2 to 4 megaparsecs, so perhaps that's an interesting place to delineate these three bins. The red shaded region, of course, is TNG 100. The black marks are Chiles. So, of course, Chiles is very different from Illustris. You can see that very obviously. That's the big takeaway from this plot. But let's take this same plot and collapse it upon a different axis. So now we have the Chiles data as the top panel and the simulation as the bottom panel. We see that, first, Chiles is much lower. We just established that. Two, Chiles seems to disagree with what we know about the local universe, and as that you get to less dense regions, you get less and less H1, which is not great. However, the simulations have what we expect. Voids have more H1. So let's ruminate on perhaps what could be wrong with our observed results. Let's not ruminate. Let's first divide it into mass bins. So I divided these into the same mass bins to see if there was any sort of relationship with that. And we find that the higher mass galaxies agree with TNG more than the lower mass galaxies, but we still again see this problem where the voids do not have enough gas. So what gives? First, our understanding of the density morphology relationship and the gaseous property of galaxies is fundamentally incorrect. We've been wrong since the 80s. Probably not that. Ha ha ha. Okay. I found that comforting, but anyways. The Chiles data is either poorly reduced or the pointing is not representative of the universe. So I don't believe that given the data quality that that would be the reason, and with some quick estimates of cosmic variance, I don't think that that would be the majority, that would be a major problem with this data. H1 stacking is clever and statistical, but can be hard to interpret. The more I think about stacking results, the more I think that this could be it, so I give this a possibly. Is that we're looking at a complex ensemble of galaxies, and so what are we actually learning when we try to take results from those? Next is how we define environment, especially at higher redshift. So when we define environment from a galaxy catalog, even one as rich as Cosmos, we are still taking an incomplete sample and trying to define the large-scale structure of the universe. So maybe it's not surprising that a simulation recovers the sort of results that we expect, and these observations don't. So I give that a quite likely. And this is fascinating work, but only represents a few data points. We need more blind H1 surveys. Definitely. I don't just say that in the need of job security. These are only 2 points, and we need to fill in the parameter space more. So again, some results, just summarizing what I said. Cool picture of the cosmic web. In the last brief part, can we actually study how the cosmic web interacts with individual galaxies? And I say, yes, a peculiar case of a galaxy. So we've talked all about ram pressure stripping. Here we have a beautiful galaxy with an obvious long H1 tail to the northeast. So, northwest, whatever. Let's talk about how this could be ram pressure stripping. Morphologically, the black dashed line goes through the center of the optical galaxy, and the H1 on the left and right side of that black dashed line are equal. Kinematically, you can see a rotation curve around the red dashed line, which is the center of the galaxy, with gas at increasing velocities, which could be parts due to ram pressure stripping. However, a ram pressure stripping purist might say the H1 is not being removed from the optical disk, and there's not appear to be compression along that axis, so maybe it's not. That's why the sum is italicized. But I really think it looks like ram pressure stripping, so I asked myself what could be causing it. And interestingly, this lies at the intersection of two cosmic web filaments. And when Dispersed was first put forward in 2011, their sort of proof of concept paper was they looked at an intersection of filaments that was not a known compact group or anything like that, and they found X-ray gas. So perhaps there is a concentration of X-ray gas here that is stripping this galaxy. And before I get shoved off the stage, here's one more pretty picture, haha, and summaries. Thank you.
30 slides in 11 minutes, very quick. Questions?
Hi, thank you for nice talk. I want to ask you about the last conclusion. Do you think that it's ram pressure stripping of interaction with entire filament, or your opinion, you think there are a group which you do not resolve?
I think the most realistic scenario would be that in the intersection of filaments, if we were to really get some deep optical images, we'd find some loose group and just a concentration of X-ray gas at the intersection of the filaments itself. I don't think an individual filament would have high enough densities to strip this much gas away.
Hi. How do your results compare with MIT stacking results at similar redshifts?
They are comparable. So Alessandro, I don't remember if he's giving a talk, but he has a very in-depth comparison between the two, and he's looked at both data sets and stacking, so he's your guy to ask. Great way to kick off a question.
There was a question down there too. Yeah. Okay, but there is somebody behind you.
The microphone is coming here anyway, so what I found more interesting is that you only find one of these cases with an H1 tail. And I was wondering, do you know the stellar mass of this system, for example?
So this is actually, so I couldn't give it a proper introduction, running out of time. This was not part of Chiles. This is a project looking at dwarf galaxy mergers for TNT H1, Tiny Titans H1. And I noticed off in the corner of this cube a beautiful H1 source, and it was this guy. So it has nothing to do with Chiles and sort of tails in that way. That being said, I do not know the stellar mass, but it doesn't seem like there's any significant star formation anyways. either in the main body or the tail, which is perhaps interesting, but it's also based off just the radio continuum.
Yeah, thank you. With regard to the gas depletion results in chilies, one of the challenges I always have in interpreting those is the depletion time is the ratio of H1 mass to star formation rate, but there's such a large spatial separation very often of much of the H1 that, you know, the depletion time in some ways isn't really a predictor. Probably a dumb question. In any of these surveys being planned, DSA 2000, et cetera, will there be any hope of resolving spatially to look for the evolution of the radial structure of the H1 to see if you directly see, you know, how the sizes of the disks and so on are evolving, not just their mass?
Yeah, so I think that chilies might be able to take a small spoon out of that question since we are resolving some of these galaxies at higher redshift. But until I think we get to the SKA era, where we both have the meerkat sensitivity, but you know, VLA A array resolution, it's going to be very hard to make those sort of determinations.
Thank you. So let's thank Nicholas again. And our last speaker before the break is Mpati Ramatsoku, talking about the H1 tails of galaxies as tracers of environmental effects.
Hi everybody. I realize that I'm standing between you and afternoon coffee, so I will try to be as light as possible and keep this short. Luckily, a number of speakers have already spoken about the things that I was going to talk about. Actually, we already had amazing reviews from the speakers before talking about H1. The work that I'm doing, I'm not doing alone. There's a whole group behind me that has contributed in various ways, and they're all listed here, some of whom I've forgotten. I'm sorry about that. I think Luca, I'd like to echo what Luca's already said, is that the picture of galaxies in falling into some environment and experiencing one or the other environmental effect is changing with time. We now know that there's a number of ways that galaxies can get quenched, and it's not only one way. I like this illustration over here from, this mic is moving, from Illustrious TNG, which shows two galaxies merging, and you can sort of pick one of the galaxies there and follow kind of the processes that it's undergoing as it falls into the center of this environment. But the main characters that I will be talking about today are the very well-known jellyfish or GASP jellyfish galaxies, 206, J201, and I will also include something about ISO 137001. These are galaxies with long optical tails. These have also been detected in H-alpha as well. They are massive galaxies. We are talking H1 stellar masses of around 10 to the 10. So massive galaxies falling into massive galaxy clusters. Up until recently, we hadn't really detected any H1 in the disks of these galaxies. I think Owen alluded to how much time is needed to be able to detect the extraplanar H1 that lives at column densities of around 10 to the 19. And so we tried to remedy this with VLA. This is the telescope I'm showing this tiny picture here with Jodie Foster listening to pulsars, and showing meerkat as well on the right-hand side. So the two gas jellyfish galaxies were observed for around 16 hours per galaxies, whereas ISO 137001 was observed with meerkat for about 14 hours. And like I mentioned, the aim was to be able to get down to this extraplanar H1. Now we get into this extraplanar H1 at resolutions of around 30 arcseconds, which is not great, but we would need many, many, many more hours to be able to improve on this, and we're working on it. This is work in progress. In these galaxies, what we're finding is that although they are undergoing RAM pressure, and in this particular case, we think they're only undergoing RAM pressure stripping as we observe them, they still retain some of their H1. We detect H1 masses of around 10 to the 9 in the gas jellyfish galaxies, although we don't detect as much in ISO 137001, perhaps because it's at a more advanced evolutionary stage. You can look at these papers over here if you want to learn more about these galaxies. So then to put this into a little bit of context, how much H1 is left in this galaxy in this plot over here. I'm showing the H1 gas fraction as a function of the stellar mass. The gray contours are from the Catinella 2018 paper. I think this is the X-gas sample of galaxies in the field or some other environment. The black line is the stacked scaling relations from Brown et al. Of galaxies of the same stellar mass or surface density as these three jellyfish galaxies, or my main character jellyfish galaxies. So now here I'm comparing it to the Catinella scaling relations and the Brown scaling relations, and what we're finding is that a number of them, or in fact all of them, are H1 deficient. So they've lost some amount of their H1. In the case of 201 and 206, they've lost around 30 to 50% of their H1, while ISO 137001, which is this galaxy that I'm pointing at here, has lost about 90% of its H1. So there isn't really much left in this galaxy anymore. So then the next thing was to try and see how the star formation rate compares with the amount of H1 given the stellar masses of this galaxy. And we've seen this plot again many times. Here I'm showing the star formation rate as a function of H1 mass for galaxies of the same stellar mass as these jellyfish galaxies. Again, these are galaxies that live in the field just doing their own thing, not being very exciting. We measure H1 depletion times that are quite low. These are global H1 depletion times that are quite low, about a quarter of what one would expect for galaxies of these stellar masses and H1 masses. This indicates that there is some enhanced-ish star formation activity for the amount of H1 that is observed in these galaxies. Of course, this picture changes a little bit when you add molecular gas, and I'm showing here in this very small plot, a plot from Moretti 2020, where they show that what is actually happening is you might be experiencing short-term gas compression. So you have this kind of enhanced star formation, H1 to H2 conversion instead, as well as maybe a short burst of star formation activity. Now this we also see at kind of resolved scales as well. So in this insert over here, which I hope you're seeing better than I am, we are showing in blue the inner regions, so the disks of these galaxies, and in red we are showing the outer regions, or vice versa. The points are the jellyfish galaxies, and we are finding that this enhanced star formation activities for the amount of the observed H1 is enhanced both in the disks and in the tails of these galaxies. So this short-term starburst is happening all over the galaxy, basically. But then what happens when you take a massive galaxy and you drop it into a small-ish galaxy cluster? For example, a galaxy like the Fornex cluster, which has a mass of around 10 to the 13. These are galaxies showing these beautiful long, thank you. These are galaxies showing these beautiful long H1 tails, which were detected through the Meerkat Fornex survey, which is led by Paolo Serra. These images are done using the multi-resolution imaging that Meerkat is capable of, or Meerkat data can do. So you can really study the details of these tails at different resolutions, and you can see the tail growing as you go to lower resolution, which is kind of what you sacrifice in sensitivity as well. So what we're seeing at first glance are just classic ram pressure signatures. You see these long tails that are radially orientated with the center of the cluster. We aren't seeing any stars in the tail, so we know this is a kind of hydrodynamic process happening. The H1 velocity gradients are also aligned with the ram pressure stripping that these galaxies are experiencing as they fall into the galaxy cluster. But if you look closer at the optical images of these galaxies, particularly only the disks, because we aren't seeing any other any optical or any stars within the tails of these galaxies, within the H1 tails of these galaxies. So what you're seeing is that these galaxies tend to have very disturbed optical morphologies, which you are seeing in these plots over here. And what this is indicating is that these galaxies might have, or might have undergone some form of tidal interaction or gravitational interactions, which perturbed the H1 out of the stellar body, after which even weak ram pressure stripping from a galaxy cluster like the Fornex cluster can easily shape the long tails of these galaxies, which is actually quite something that was quite nice to see. So now we can play the same game, look at the H1 compared to normal galaxies in the field. So the galaxies with tails in these particular plots would be the ones that are yellow and red, and I'm running out of time, so I will try to be fast. And what we're seeing is that, yes, indeed, they are H1 deficient, so they've lost some of their H1, but unlike their counterparts in the big clusters, they don't really show this enhanced star formation activity for the amount of H1 gas that is in these galaxies. So perhaps you need these huge clusters to compress the gas, as simulations have been suggesting, and form this short-term starburst. I won't talk about this because I'm running out of time, but I want to say that I've only been talking about a handful of galaxies, but we are increasing the sample to try and understand how these galaxies form in a variety of environments from the MGCLS catalog. We aren't really seeing anything much yet. And so I'll just leave you with this summary, which shows that in large clusters, you can pretty much remove gas, the cold gas reservoir from galaxies just with ram pressure, and you can do that all over all stellar masses. But then in small galaxy clusters, it seems like you need some gravitational interactions, like tidal interactions, to disturb the H1 and then be able to remove the H1. As to how these H1 form, we don't know yet, basically, and I'm hoping that we'll find out something about orbits from Andrea Viviano, who's sitting somewhere later today. Thanks.
Questions for Mpati?
Thanks for that nice stuff, Mpati. So the evidence of tidal interactions, do you see it, I may have missed this, do you see it in the kinematics too?
Oh, I forgot to mention, we haven't really done a kinematic study, so that's one of the next steps, and I think we will be able to see that as well. But what we've mostly been looking at is just the optical disks. So we see this very disturbed stellar bodies with pockets of star formation activity happening at previous regions.
Thanks.
Luca?
So what is the fraction of galaxies that you detect in H1 that show tails?
Okay, so these were the slides that I wasn't showing. For example, in the MGCLS catalog, we detected around 900 galaxies, and only about 170-ish of those showed H1 tails, so it's not a huge fraction, yeah. No, not all of them are members. They're in the field.
Time for one last question. If not, okay, let's thank Patty again. So now it's coffee break, back in half an hour.